Hello and welcome to our soil mechanics presentation. In our brief, we were asked to design an earthen dam. Earthen dams are used to hold back water for a number of reasons, such as hydroelectric power generation, water storage, and flooding prevention. In the case of our brief, the dam would be used to hold back flooding from the Thomond student village, which, as the picture shows, has come dangerously close to flooding in the past. Finding the correct site levels and flood levels is vital to the success of the dam. We use known levels on site where possible. If there is no known level on site, we can use online facilities like CFARMS or the Office of Public Works topography maps. To find the height of flood to be prevented against, we use flood level data from reliable sources such as Met-Éireann or the OPW flood maps. Site investigation. During site investigation stage, suitable borrow sites would need to be selected to excavate the soil used in the dam. Trial pits are dug to establish layers or strata in the soil, both at the construction site and the borrow site. Site reconnaissance must also be completed to check for services present in the area, such as water mains, gas lines or ASB cables above or below the ground.
In order to know if the soil from a trial pit is suitable for construction, it must first be classified. Firstly, a sieve analysis is conducted. This dictates if it is a fine or coarse-grained soil. To create a complete graph, a sedimentation test must be done. Atterberg tests are done by varying the moisture content to find if the soil is brittle, semi-brittle, plastic or liquid. By plotting the liquid limit against a plasticity index on Casagrande's chart, we can classify it as a silt or clay with a low, medium or high plasticity. Failure modes of an earthen dam include slope failure, sliding, overtopping, piping and bearing capacity. Slope failure is prevented by classifying the soil and reading the slope ratios off a credible source. Sliding of the dam is not covered in this module.
Overtopping occurs when the water level surpasses the dam height. This is a catastrophic failure, resulting in rapid erosion of the dam.
In order to determine the seepage in an earthen dam, a flow net must be drawn and a permeability test undertaken in the lab. The permeability test can either be the falling head permeability test for fine-grained soils or constant head permeability test for coarse-grained soils. Following the permeability test, a flow net must be drawn on a scaled drawing of the dam. The phreatic parabola is the first flow line drawn. This must follow the following rules. The length GC must be equal to 0.3 times the length HC as shown in the diagram. And the points drawn on the curve must obey the equation x is equal to x0 minus z squared over 4 times x0, where x0 is a constant. Following this, the further flow lines must be identified and drawn, approximately evenly spaced. Equipotential lines must be drawn, crossing flow lines at right angles to give circular squares. From the flow net, the number of flow channels can be determined and the number of equipotential drops. Thus, seepage can be determined by the equation Q equals K times delta H times NF over ND, where Q is the seepage, K is the permeability, delta H is the change in total head, NF is the number of flow channels and ND is the number of equipotential drops. Piping occurs when water seepage develops channels in the dam. The factor of safety of piping due to boiling may be calculated using the flow net. Factor of safety for piping due to boiling is equal to the critical hydraulic gradient over the maximum hydraulic gradient. The critical hydraulic gradient is equal to the unit weight of saturated soil minus the unit weight of water all over the unit weight of water. The unit weight of saturated soil is equal to the saturated density times gravity. The maximum hydraulic gradient is equal to delta H over L, where delta H is equal to the change in total head over the number of equipotential drops, and L is equal to the shortest distance between equipotential lines. The maximum hydraulic gradient is typically close to a filter in an earthen dam or on the downstream slope of a dam. The factor of safety may be increased by widening the dam, which is costly, or by adding a filter. In order to design a filter, D15 of the filter over D85 of the soil must be less than 4 to avoid loss of dam material through the filter. D15 of the filter over D15 of the soil must be greater than 4 to avoid build-up of seepage force in the filter. And D5 of the filter must be greater than 75 micrometer, and D100 of the filter must be less than 80 millimeter.
A bearing capacity calculation is necessary to determine if the foundation material on site can support the proposed dam. Firstly, we determine the allowable bearing values of the foundation material. IL in this equation is the liquid index, WN is the natural moisture content, WP is the plastic limit, and IP is the plastic index. The liquid index found determines whether a material is a hard, stiff or medium clay, and then max allowable bearing capacity can be found from literature. To find the stress applied, we use rho saturated. Since the saturated unit weight of soil is rho saturated times gravity, we multiply by 9.81 meters per second squared. Then the stress applied is equal to the saturated unit weight times Z, where Z is the height of construction material acting on the foundation. Finally, we must show that the stress applied is less than the stress allowable.
Before constructing, the area on which an embankment is to be placed should be cleared of all vegetation, such as trees, logs, stems and roots of trees, etc., and other objectionable material which cannot be properly consolidated or will not support the load of the embankment or structures.
So we used the Proctor test in the lab to calculate a dry density value for the soil. We then used 95% dry density max value to get our range of values for our soil to get correct moisture content and density values that we could use on site. Most common practice on site is to use a sheep's foot roller, as this gets the required compaction level that is required. It is also common practice to use 225mm lifts or layers. In the construction of the dam then, we had to take into account the settlement of the dam itself. The dam will settle roughly 5% of the height. For example, our design height would be 3.74 metres, with the construction height being 3.93 metres. For the quality control aspect then, we looked at the most common practice would be CBR and MCV values. These are very expensive means of calculating the correct density and moisture content values. It is more common practice to use a sand replacement test and a nuclear density meter to get your correct densities and values on site.
After constructing, regular maintenance and inspections are required to ensure it remains in a good operating condition. Seepage from dam should be monitored on a regular basis. An increase in seepage may lead to piping failure.